This video is on the introduction to the probability theory. So what do you need to know about probability? So in the intro, first of all, you need to know the rules of any normal probability distribution, so that as you go on in those other expanded topics of probability theory, you'll be able to apply the concepts that you will learn in this intro, video. So let's get underway and get started to know what you need to know about the probability theory. So first of all, the probability theory, first of all, has got some rules that probability can never be a negative. That's the first thing to take note. It's never a negative. It's always positive. So this simply means, okay, probability can never be greater than 1. I'll use the symbol just. That symbol means greater, can never be greater than 1. Take note of that. And then if you are adding probabilities, most of the time, take note of this, if you're adding probabilities, I'll just abbreviate with P. If you're adding probabilities, you should always equal to 1. So another rule to take note of in probability theory. So they can never exceed 1. They will just be, either less than 1 or somewhere there. It's between just what you just need to know in short is that every probability is between what? 0 and 1. That's all. And that's it. So those are the first main rules of the probability theory. Okay, so now what next? So you now need to know the general formula that we use for, should I say, any probability distribution. So what you should know is that the probability of any events to occur, right? In this case, I've just put A. Maybe they'll tell you what's the probability of event A occurring, right? It's equal to N of A. I'll explain. And then divided by N of S. What do they mean? N of A just simply means, should I say the total number of that desired outcome? Total number of that desired outcome divided by the total sample space. So the one on top is always like the desired outcome, meaning the event that you want to occur. For example, you might be, should I say, flipping a coin, for example. What are the chances that you want that a head will drop if you flip a coin? The desired outcome is what? You want a head to drop once you flip a coin, right? So the N just stands for like the number. So if you look at a coin, right? A coin only has one head and one tail, right? And if you want a head, how many heads are possibly going to drop? Just one, right? Yeah, and that's what they mean by N. Just the total number of that desired event to occur. Yeah, so if you look at that example of a coin, like we just said, you want the head to drop, meaning what is the total number of that desired outcome, which is the head? It's only 1, so you would put 1 there where there is N open brackets A. What about on S? S stands for the total sample space. Sample space is just the number of possible elements in a given experiment. That's what sample space is. So if you look at a coin, what is the sample space of a coin? It's just a head and a tail, just 2. In short, just a total number of possible outcomes in a given experiment. So a coin, as we just said, has got 2. There's a total sample space, meaning what will substitute below number of the sample space, just going to be 2. And that's how you get probabilities of an event to occur. So just take note of this example we have used of a coin. It's very, very realistic. You might ask yourself this question also. Let me just write it down. Like they might ask you, what is the probability? What is the probability? I'll just be abbreviating it, of getting of getting a 5 when you throw a die. When you throw a die. So think about the die. What's a die? A die is just a 6-sided cube. Most of you guys, if you've maybe used the die before, those which are used in certain games, and whatnot, that 6-sided cube is called a die. So they ask you, what is the probability of getting a 5 when you throw a die? How do you answer that? Remember the general formula always, its probability of that event to happen is always equal to the number of that desired outcome that you want over what? Over the total sample space. Just always remember that when you rewind this video, you'll find the general formula. So you want a 5. You ask yourself, how many 5s are there on a die? There's only one 5, because a die, we said it's a 6-sided cube, which will just have one of each number, in short. So if you want a 5, the total number of that desired event, which is a 5, is just 1, right? So you just say, okay, it will be equal to 1 over what? The sample space, right? Is a number of the sample space, so the formula states. If you look at a die, we just said it is a 6-sided cube, meaning how many possible outcomes are there? That's what sample space actually just stands for. There are actually just 6 possible outcomes, and that is what you divide here. So if you've noticed, we're just working in line with the general formula just to get to understand the probabilities of events occurring. And that's how we answer probability questions. So now, I wanted to now introduce what they call the additional rule to probability theory. Additional rule to probability theory, that's the next heading here that I'll introduce. So the additional rule, okay, just write that well, additional rule. So under this additional rule to probability theory, we get to talk about what they call mutually exclusive events. Mutually exclusive events. That's one of the headings under additional rule. So under this, should I say this theory, we bring in a little bit of that knowledge we had learned in sets. If you remember in your mathematical analysis, that sets, that topic, it comes to apply here again in the probability theory. So what do they mean by mutually exclusive? Well, that just simply means that if you have maybe event A, and you might also have maybe, or let's just say, or event B, meaning these two events cannot occur at the same time. That's what mutually exclusive just means. So we get to calculate the probability also of mutually exclusive events. Yeah. So how do you know you're being asked a question on mutually exclusive events? So most of the time, first of all, what you might be asked is that, okay, maybe the probability of A occurring is, maybe they'll give you a certain figure. Then they'll ask you, what is the probability that A will not occur? So that's just showing that they're trying to give you a certain scenario of, okay, maybe if this one occurred, then another event will not come through and occur. So I'll give you an example. Actually, that's what I want to do, so that this part for mutually exclusive events can actually just make sense. So let me just first of all share the general formula that we use under the additional rule, specifically, of course, with mutually exclusive events. So, well, the probability of any given event to occur should be equal to the probability of maybe event A plus the probability of event B minus the probability of A intersection B. So that should be B at the end there. I hope you'll be able to just see it. I said A intersection. And maybe just rewrite it for the sake of maybe those that might not be able to see it. So I said probability of A intersection B. Yeah, that's what's at the end. That's the additional rule. This is the formula we use. Yeah. So before I go to an example, let me just quickly also introduce one more rule so that at least when I got the examples, we can handle two examples. So this is for additional rule, meaning as we said, you have two events, for example, maybe A and event B. Then if you've seen from the formula, there's obviously a possible event A, event B, and then they've said minus P intersection A and B. Why have they said that? What does that mean? What does intersection mean from set theory? Because we said this part actually requires knowledge from set theory. When they say intersection, that just simply means that you're trying to find the common points between A and B, right? If you remember from sets, what does A have in common with B? But what does mutually exclusive mean? A and B cannot occur at the same time. Meaning, if you make them an intersection, then at some point they'll have something common, if you get the logic behind there. So that is why we subtract anything that might, should I say, that might try to relate A and B, because when it's mutually exclusive, they cannot have anything in common. That's why there's always minus, okay, probability of A intersection B. So all these will make sense when we get to see some examples. Let me just talk about one more rule before I go to the examples. There is what we call the complement rule. Complement rule. What does that mean? Again, some knowledge from your set theory as well. Complement. Let me just spell that. Complement rule. Okay, this one just simply means that, like we used to do this in sets. When they say complement, we used to put a certain sign like on the top of a letter. Okay, that's a symbol there we put against the letter, just stands for complement. This is just revision from sets we're doing right now. So this rule under probability just states that the formula actually for complement rule, is that when you're finding the probability of a certain event, maybe let's say event A, you have that the probability of event A occurring plus event A not occurring should always equal to what? 1. That's the rule for complement. So you just have like one particular event and it will be making sense. So when there's complement rule, most of the time they'll just be talking about one event. They'll tell the probability of this event occurring is maybe 0.5. What is the probability that A will not occur? So you just know that, okay, we're talking about one event. They've told me that, okay, if it occurs, it's 0.5. Meaning if it does not occur, what would be the figure? You'll just be like, okay, from what they said in complement rule, it's that if I add the probability of that event occurring plus it not occurring, they should always add up to 1. That's just the complement rule. So you just remember this. Usually there's only one specific event they would be referring to. So you just know that, okay, if they've given me, okay, the probability of A occurring is this. What about for it not occurring? You just know that, okay, I know they're adding up to 1, so you like just change the subjects of the formula and get for the missing figure. So let's go to some questions and see what we're all talking about. Okay, here. Let us revise this one. Example 2. A group of 20 students contain 8 who are in the first year of study. A student is picked at random to represent the group at a Senate meeting. Find the probability that the student picked is not in the first year. Find the probability that the student picked is not in the first year. What event is being talked about? A group of 20 students. Okay, so whenever you've seen such questions, try to identify what event is being talked about here. So we just said the 20 students are just the total. What have they just said? 20 students contain 8 who are in first year. Okay, that's the event they've just told us, first year. A student is picked at random to represent the group or the Senate meeting. Find the probability that the student picked is not in the first year. So you've seen they talked about first year, and then here they're saying find the probability that that student again is not, maybe that they will not be a first year student. So the event first of all being talked about is that they are first year students they were trying to examine. Okay, if they pick a first year, okay, they are like, okay, about 8 out of 20 first years. That's the probability of choosing a first year, 8 out of 20. And now they tell you that, okay, what is the probability that they will not pick a first year? So if you've grasped that concept from complement rule, as I said, it's usually one event being talked about throughout. They'll tell you, okay, the probability of choosing maybe A, or in this case, a first year student. What's the probability that again they will not choose this student? So we just remember that, okay, the probability for such a scenario, we just know that the probability of picking such a first year student plus not picking them should add up to 1. That's a theory we use. So if you look at this, 8 out of 20 is the probability of choosing a first year student. Okay, so let's just go to our screen and find this. So we said 8 out of 20. That's the probability of choosing. I'll just say let first years be equal to A, event A. Like you just want to label them to simple letters to easily compute. So we've just let the first years to be equal to event A, and we've said, okay, the probability of choosing a first year student, they said there are about 8 of them out of 20, meaning 8 out of 20 is a possible chance of choosing a first year student. Then what about probability of not? So you just say, okay, this is the formula I'm going to use. 1, we said they should always add up to 1. Probability of what? Choosing that student. You just say P, open brackets A, plus probability of not. When I put a certain, it's like a comma, something like is it a comma or an apostrophe? Yeah, that just simply means not choosing that person. So we just know that they should add up to 1. That's what the complement rule is. It usually has one event. So if I start substituting in my formula, 8 over 20 of choosing plus this one of not choosing, I'm not sure. We just put that. Then you say 1. Change the subject of the what? Of the formula here. You'll find that when you change the subject of the formula, the probability of not choosing will give you 12 over 20 when you compute this. So that's the answer, just like that. And that's how we know that, okay, this is the complement rule. Let us look at another example. This time around, want to see an example for mutually exclusive events. If you look at the screen there, of course, there's been some summary, as you can see above, of mutually exclusive events and how they do apply to the additional rule. But my prime focus, okay, is on the one written example 3. Example 3. Yeah, let's try to focus on example 3, which says a die is thrown once. What is the probability of obtaining a score of 3 or a score of 5? A die is thrown once. Okay, so you're being asked to find the probability of obtaining a 3 or a 4 or a 5, sorry. Is it possible to get 3 and 5 at the same time? No. If you have really followed this is an application of mutually exclusive events. Why do I say that? Mutually exclusive events, we said, are events, you'll usually give you 2 events in a question, and a mutually exclusive event is an event that cannot occur at the same time. Take note of that. You're looking at a die, 3 and 5. Can they really drop at the same time? Like if you throw a die, you think you'll be able to get a 3 and a 5 like on top of that die? It's impossible. That is why I'm saying this is an application of mutually exclusive events. So they won't always tell you in a question, it's you to reason. That's why the probability theory might look tricky, but it's just all about reasoning. That's all. So 3 or a 5. Okay, so what do you do? What is the formula we use? Having known that, okay, this is an application of what? Mutually exclusive events. I'll write the general formula yet again. And I'll state one thing just after as I write. So this is the general formula we use for mutually exclusive events. maybe event A, we said there are usually two, or event B, minus probability that of course maybe A and B can be combined. So take note of this rule I'm about to show you. This part where we're putting A intersection B, we said it's like a point where maybe A and B might have something in common or happen at the same time. In short, that's what that means. But we said in mutually exclusive, this condition does not exist. We said event A or B can never have anything in common. So usually what they say is that once you've identified that it's a mutually exclusive event, this part just let it be equal to what? 0, because you know they cannot happen at the same time, if you get the point. Then what about probability of A, okay, plus probability of B? So we said there are two events. So what happens is that you get a probability of the first event plus a probability of the second event, then you add them together. Another tip, the words they use can also guide you to know that, okay, I'm just going to use this formula, which is of course additional rule. Additional rule contains the same formula which is in mutually exclusive. They're one and the same thing. Yeah, so if you hear words like or, A or B, something like that, this word I'm circling here, then you know that you're going to use this formula that is just on the screen. So just to pay attention, then you're safe most of the time. Pay attention to the keywords. Okay, so let's solve this question. We said, what's the probability of getting a 3 or a 5 on a die? So you ask yourself first of all, what is the probability first of all getting a 3? Let's solve them separately. A 3. So we said, looking at a die, it has 6 sides, so the sample space is just 6. So you know the denominator there where there's usually that probability is equal to, you know, we said the total number of that desired outcome, which is a 3. We said there can only be 1 3 on a die, meaning the total number of that desired outcome is just going to be 1. Okay, what about, we said denominator sample space, which is just 6. So the probability of getting a 3 is 1 over 6. You've answered. Plus what? Probability of getting a 5. What is the probability of getting a 5? There's only 1 5 on a die, so it's like going to be 1 again over what? The sample space of a die. So you just find yourself that you have the same probabilities for both, because okay, they're just coming from the same object, that's why they've got similar probabilities. So when you add these two, then you have answered the probability of getting a 3 or a 5, which is going to be, this is supposed to be about should we answer this roughly, is it 2 over 12, which should be reduced further. Yeah, if I'm not mistaken. Let me just punch it quickly on my calculator. So I've punched it. Actually, it's supposed to be 1 over 3 is the answer. Yeah. So what have we just said to summarize? Usually, to know that mutually exclusive events is being applied, we look at what what they're asking. Most of the time there are two events, first of all, two events that are asked in a question. Then you look at how they've asked them. 3 or 5, you reason, can 3 and 5 honestly appear at the same time on a die? Of course not, because mutually exclusive events are events that cannot occur at the same time. And that's how we know that, okay, mutually exclusive events, okay, they are there, or this question is on that. And this is the formula you use above. Take note that P intersection, that P open brackets A intersection B, we said it's equal to 0 in this theory. Why? A and B, A intersection B just means that A and B should happen at the same time, but mutually exclusive events denies that rule, if you've understood the concept. So we just remain with PA and PB, yeah, to calculate the probability. Then I even added one more point. I said when they say or like A or B, something like that, that just simply means additional rule is being applied also as well. So additional rule, mutually exclusive events, they have one and the same formula. These are just like guides. Okay, if you've missed that, is this really mutually, you use the other word, the or, you know that, okay, yes, you're landing in the same formula, and that's it. One more thing, you can have what they call non-mutually exclusive events. Take note of this, non-mutually exclusive events. This is going to be very interesting, and I'll show you one Good example. Non-mutually exclusive events. What do we mean by this? Well, this is just the opposite of what we're just from doing. Non-mutually just simply means events that can actually happen at the same time. Whether there are two of them, they can actually occur at the same time. Just get that concept. This theory as well is an application of the additional rule, meaning the same formula you're seeing above works. But take note of that. Take note of this part. I wanted to just mention this. This time around, that's this part I'm circling right now. The P open brackets A intersection B is no longer equal to 0, right? If you get this point now, it's no longer equal to 0 because A and B can actually now occur. So it will have a certain value this time around. Yeah, that's something take note. Don't confuse mutually and non-mutually. So let's look at an example quickly. So we are now looking at example 6 on the screen. 20 identical discs are marked 1 to 20 and placed in a large box. One disc is drawn at random from the box. Find the probability that the number on the disc drawn is either a multiple of 2 or a multiple of 5. Okay, just from analyzing this data, we're trying to calculate, of course, the probability of drawing a number that is a multiple of 2 or a multiple of 5. So one thing you should obviously take note, they've used the word what? Or. It's there. Meaning that formula we wrote when you run it's coming to work, the additional rule formula. But let's try to understand first this to know whether, okay, do you think we're also going to have a mutually exclusive event kind of scenario, or there will be a non-mutually exclusive event kind of scenario? Let us first go through and interpret this information. So let's go back to that screen. We are back on this same screen now. We're trying to, this is the formula, by the way, that we'll work with, because as we said, once you just identify those keywords like or, let's just know that this formula from additional rule is being applied. Multiples of 2. What do they mean? So multiples of 2, just like those numbers that 2, 4, you multiply by 2, such numbers 2, 4, numbers that 2 can go into without leaving a remainder. I think that's the simplest explanation I can put. 2, 4, 6, 8, 10, 12, 14, 16, 18, and 20. Those are multiples of 2. What about for 5? Numbers that 5 can go into and itself. 5, 10, 15, 20. Look at those numbers. Do you see any common points between these two particular events? If you're able to see two common numbers that are matching, then we are applying non-mutually. If you are getting the concepts now. If there are no similar numbers in each two events, then these two events are what? Mutually exclusive. That's all. We just apply in probability. Questions will never come directly on a silver platter that okay, this is a non-mutually exclusive event. We just apply. So if I look at my information, I've seen that 10 is repeating in that one and here. Okay, that's already one of the elements has repeated. I've taken note 1. Is there another number? If we check 20, I've noticed 20 is there and 20 is also there. So at least there are about, should I say, 2 repetitions from the 2 events. So you take note that, okay, even though these events, they look like they were separate, they're actually 2 repetitions, meaning they do have something in common. So thus, we are actually we are actually applying non-mutually exclusive events. So what you're going to do here simply is that you're going to now say and try and substitute in this main formula. So look at event 2 first of all alone. What is the probability of event 2 occurring? Choosing a multiple of 2. Go back to the general formula of probability. As we said, that general formula, never forget it. It's always equal to probability of an event to occur is always equal to the number of that desired event over the total sample space. So you're trying to get the probability of picking a multiple of 2. How many multiples of 2 have we listed here? And they should be up to 20, so that was the range they gave us. Apparently, if you count those, they're about 10. So they said that's the the probability, first of all, of picking event 2, the general formula says the number of that desired event, which is about 10, so you put 10 on top there, divided by what? The total sample space. What is the sample space? They told us that there are about 20 disks, so that is the sample space, so it's like 10 over 20. So take note that for event 2, the probability for event 2 is 10 over 20. Welcome, right? That about 5. Event 5. What is the total number of that desired event of picking a multiple of 5? You count these, they are about 4. So it's going to be like 4 over what's the sample space? 20. So you have already your 10 over 20. You have your 4 over 20. And you also have two events that are, should I say, two events that were common. They will also make up a certain probability that, event A and event B, which in this case event 2 and event 5 have something in common, which will be substituted where there is A intersection B, and I'll be even explaining. So this is how you will record. You go there on your general formula. First of all, you state your general formula. Let's say multiples of 2 will take event A. We said for multiples of 2, what was the probability? 10 over 20. Plus, what about for B? We said, okay, B, let's say B will take the picking multiples of 5. And for 5, we said how many? What's the probability? 4 over 20. Minus, is there a chance that multiples of 2 and 5 had something in common? Yes, we picked two numbers that had something in common. So you make a probability of, for event 2 and event 5 having something in common, which is just 2 out of what? The total sample space, which is 20. That's how we reason. And then you just easily compute this and try to get your answer for the probability of picking multiples of 2 or multiples of 5. So that's just how you analyze given the data. So I'll just advise you rewind, you rewatch to just grasp these concepts, because they are very crucial as you start going deep in this probability theory, should I say, topic. Yeah, so let me just punch quickly. I want to just see what answer I'm going to also get. Okay, so we said 2 over 20 that side. Trying to punch. Okay, I'm getting 3 over 5. That's my answer. So you've answered the question. What's the probability of picking multiples of 2 or multiples of 5? The answer is 3 over 5. As you have seen how we have analyzed, first of all, we said we saw a keyword that was or. Or means we are applying this formula above for what's this additional row. Next, what did we pick? We said, okay, they've told us multiples of 2, we listed them. Multiples of 5, we also listed them. We asked ourselves, do these two have anything in common? Yes, they do. They had about 2 digits, which was a 10 and a 20, that had something in common, which satisfies this part of the formula that I've circled, where it just says, is there any common or similarity between the two events? We said, yes, there were 2 numbers out of 20, and that's what you substitute there. Yeah, and of course, we compute the overall probability of either a multiple of 2 or 5. So that's just how we reason in the probability theory, and I hope this video will give you some, should I say, some good intro and some understanding of the probability theory.